Second? Okay. Hi, everyone. How are you?
Good.
Great. Thank you very much for having me come to speak with your club this evening. My name is Nathaniel Frissell, and my call sign is Whiskey 2 November Alpha Foxtrot. And I'm actually a local person, fairly local. I grew up in Bloomfield, New Jersey, so just a few miles from here. And I've had a pretty interesting career in and because of ham radio since I grew up. I did my undergrad at Montclair State University, and I did some ham radio activities up there. And then I really got into ham radio, and I eventually earned my PhD from Virginia Tech in ionospheric physics and electrical engineering. And so that's led me to the career that I have now. I'm currently a postdoctoral research associate at the New Jersey Institute of Technology, where I'm also a member of the W2NAF Club, which Josh just talked about. And we have a few audience members who come very graciously and help out with our VE sessions there. Jerry and Walter, they come out and help us with that. So that's a little bit about who I am. And I'm here to talk to you tonight about HamSCI, the Ham Radio Science Citizen Investigation, and the 2017 Total Solar Eclipse. So I'm the first author here. I also have other people on here. Magda Moses is a student at Virginia Tech. Greg Earl is a professor at Virginia Tech. Ethan Miller, Steve Kepler, Josh Katz, Andy Gerard, these are all hams from different places. The Reverse Beacon Network team, the people who make the Reverse Beacon Network run. And there's actually probably more people who have also contributed to the material that I'm going to be talking about tonight. So the first thing I want to talk to you about tonight is ham radio and space weather. And sometimes I give this talk to astronomers, astronomy clubs, so they need a little bit more of an introduction on ham radio. But even people who've been ham radio operators for a while or just a little bit, they may not know a lot about the connection between ham radio and space weather. And I'm going to start off by just saying this is how I got interested in this. This is my ham radio shack at my house. It's a pretty modest station. When I took this photo, I have a TS-830 and I have a CAZU-857, which is actually on display in the back there as part of our live demo. Now I have a ICOM IC7410 as well. I've got a G5RV antenna. So it's pretty nice. And as most of you know, ham radio is a hobby for communicators, builders, and experimenters. And it's a really wide-reaching demographic. I mean, we have people from all ages and all walks of life. I'm really happy to see a number of younger people in this room too, as well as people with a lot more experience. In the United States, we have over 730,000 hams and about 3 million worldwide. And that's really important because some of the people I talk to are people from the science community, and I'm trying to sell that, this is a citizen science project. So it's important to know that we as ham radio operators, we're a big, strong community. My primary interest is the HF ham radio bands, which span from 1.8 megahertz all the way up to 28 megahertz. And then we also have the 50 megahertz band here as well in the VHF band. And these have wavelengths between 160 and 6 meters. So this covers a large spectrum and a large change in wavelength. And what's important about this is you'll see in a minute that these different frequencies behave very differently as they travel through the ionosphere. Whether if the ionosphere is stronger as during the day or weaker as in at night, they'll behave differently. They'll propagate differently. Many of you are very aware of this as you participate in contests, as you participate in field day, as you get on the air regularly. You're aware of this sort of thing. This is the Ham Radio Club at NJIT, K2MFF. You can see some of our students there operating during one of the contests. So one of the tools we have for understanding how radio waves can propagate through the ionosphere is a tool called ray tracing. Ray tracing, so the ionosphere is made up of, is part of the atmosphere where ultraviolet energy from the sun knocks electrons off of neutral particles, neutral atmospheric particles. And then those electrons float around and they're negatively charged, and then you have the positive ions from those particles. They're floating around, and they don't necessarily reconnect right away. And what this results in is an electrically charged gas. and you can actually compute what's called an index of refraction for a particular frequency as a function of your electron density. And just like in regular optics, if you have a change in electron or an index of refraction, a gradient in index of refraction, that will cause a bending of the light rays. So the same thing is true with your HF rays. That's how things go up to the ionosphere and then bend back down. And so we can use a ray tracing program to calculate or predict where we think these rays will go. And these two diagrams, the one on top and the one on the bottom, show two cases of this. The one on top is for a 15 megahertz signal, and on the x-axis we start at 0 kilometers. That's where our transmitter is located, and we're going out to about 2,000 kilometers away from the transmitter. And then the axis up on the y-axis goes from 0 to 500 kilometers altitude. And we have this 15 megahertz transmitter sending out a ray, a fan or of different elevation angles, and you can see where these different waves go. Some with higher elevation angles end up cutting out into space. Some with lower elevation angles will get refracted back down to the ground, and here they're hitting around 1,500 kilometers altitude. The colors in the background represent the electron density. So brighter colors like these reds mean higher electron densities. This is your F region ionosphere here. These darker colors represent lower electron densities. Down here at the bottom, you have your D and E region ionosphere. So your regions of the ionosphere from lowest to highest are D at the lowest, then E, and then F, which sometimes splits into F1 and the F2 layers. In the bottom figure, we're showing the same ionosphere, except looking at a 10 megahertz signal. And so you can see the behavior is very different. You're still getting refraction, but now you actually get more bending. So the lower you go in frequency, the more the ionosphere is going to bend those frequencies. So here you can see we actually get 2 hops at 10 megahertz in about the same space that we have with 1 hop. And as we've mentioned before, and as you're probably aware, the ionosphere is stronger during the day because you have UV rays from the sun creating the ionosphere. It's weaker at night. The ionosphere does not go away completely. It's still there. And so during the day, you'll be able to support bending of higher frequencies. So during the day, you can probably bend these 15 megahertz rays down. But at night, they might escape into space. So this is very interesting from a science perspective because these ham radio signals go through the ionosphere and can tell us something about what the ionosphere is doing. And the ionosphere is controlled by activity out in space, not just from the sun, but also from the way the Earth's magnetic field moves. And it moves around very dynamically in response to solar events, in response to auroral activity. And so all of that stuff can affect the radio signals we see on the ground. So science is trying to understand how the world works, how the ionosphere works, how it's connected to space. Ham radio generally wants to talk from one place to another. Now let's jump to a slightly different topic in ham radio for a minute, and that's something called CW Skimmer. How many people here have heard of CW Skimmer before? We've got it. Okay, a few people. How many people here have heard of CW? All right, a little better response. That's good. It's much better than the astronomy clubs I reach. Now, how many people here are CW operators? Okay, so you've got a few people. So what CW Skimmer is it's a program, a computer program that will actually decode Morse code for you. Now, if you're an old school CW operator, you may be like, oh no, I want to do everything by ear. My ears are a much better copy than the computer. And you know what? That may be true. But we can actually use CW Skimmer as a different tool rather than just as something to help you copy CW. One thing that's neat about here is, do you see how many Morse code signals this is capturing all at the same time? It's capturing a lot. It's a fairly significant amount of bandwidth. And this is only looking at maybe like 10 kilohertz worth of space, maybe 5 kilohertz worth of space. And you see a lot of different signals here. Now, no matter how good your ear is, you're not going to be able to copy 10 kilohertz worth of bandwidth all at the same time. much less maybe multiple bands all at the same time. But with a program like this, and with a software-defined radio, you can maybe listen to all of the ham radio bands at the same time and know all of the people who are calling CQ on those bands simultaneously. And that's one of the things CW Skimmer and its counterpart program CW Skimmer Server can do in conjunction with a software-defined radio, which I have in a live demo over there, so you can see that after. And so now you can know everyone that's on the band all at the same time. And if you write another program, how many people are familiar with DX cluster in the spotting networks? We've got a few hands. So a spotting network is where a ham radio operator says, I hear such and such a station, like let's say this Russian station, and I want my friends to be able to know that they're on the air on 14.030 megahertz as well. So I'll go to this computer network and type that in, and then boom, they broadcast a message out to all the other ham radio operators on the cluster, and they'll know, oh, I can go look at 14030, I can work this Russian station, and I don't have to go, noodling around, tuning around, trying to find them. I can just go work them. So in the past, like up until, say, the mid-2000s, this was all done manually. People would type in those spots by hand. But now you can take a program like this, CW Skimmer and CW Skimmer Server, and you can make an automated DX spotting system. And that's what some people have done. There's a number of people completely independent of me. They were doing this well before I started getting into this business. They invented this website called the Reverse Beacon Network. It's called the Reverse Beacon Network because instead of having transmitters, known transmitters send out signals about propagation, what they do is they set up networks of receivers to listen to people who are transmitting and record what's going on. So you can go to this website right now, even on your smartphone, and you can see a real-time feed of spots, Morse code and radio teletype spots from around the world, telling you what frequency they're on, whether they're calling CQ, what their signal-to-noise ratio is, and how fast they're operating CW. And they'll give you a nice map of this, and they record all of this information to their website, and they archive it so that other people can come along and study it later. Because how many people here have heard of solar flares? We've got a bunch of them. Are solar flares generally good or bad things for ham radio? They're generally bad, yeah. So a solar flare is one example of what's called a space weather event. It's an event that usually starts at the sun and somehow influences the our radio communications, the space environment. So I came along and I saw this data set and I said, I'm a grad. When I was a grad student, I was using data from high-frequency radars to study the atmosphere. I'm like, I wonder if I can look at their data archive from the Reverse Beacon Network and see space weather influences in this data set. And sure enough, I was able to. My friends at NJIT encouraged me to go write a little article about what I found, and I was able to show examples of solar flare effects in the Reverse Beacon Network data. And so I went first and I looked up data from a satellite called the NOAA GOES satellite. That's the Geostationary Operational Environmental Satellite. And these are generally weather satellites, but they are also what measure the X-ray energy from the sun as it hits the Earth. And so this is what they use to actually measure the solar flares and whether or not they're going to be important to what happens on Earth. So I found something called an X-class solar flare on May 13th of 2013. And then I went to the Reverse Beacon Network site and I plotted the data about a half hour before that flare started. And you can see there's lots of QSOs going on. So the green is 7 megahertz, the yellow is 14 megahertz, the orange is 21 megahertz, the red is 28 megahertz. And you can see all sorts of good QSOs are going on. And then right at 16:05 Zulu time, 16:05 UTC, bam, we get this solar flare. And what happens to all the QSOs? They go away, right? And so you can see this beautifully in the Reverse Beacon Network. And what happened with the solar flare is we know that this is called a radio blackout. And what happens during a solar flare is you get all of this X-ray energy penetrates deep into the atmosphere, into the D region ionosphere. And that's a special region of the ionosphere because instead of having the electrons there refract the radio signals back to us, before they get a chance to re-radiate the signal, they'll collide with a neutral particle, and their signal will get damped. And so that's why the D region absorbs our signals. So you can see that the solar flare happened over this part of the US, so the QSOs on the western part and central part of the US disappeared. Many of the ones between Europe and the US disappeared. There's still a few there. Everything to South America disappeared, and it just went away. And if you look at the reverse beacon network data, later it gradually gets better and better. So this is a really nice example. And I was actually able to get this published in Space Weather Journal as a feature article. So that was really nice. Some other ways you can look at reverse beacon network data. How many people, anyone here, operate November sweepstakes? A couple people. It's a really fun contest, domestic contest. So this is data from the November sweepstakes CW back in 2014. And here I have the number of spots that the RBN saw as a function of time for the contest weekend. So this is Friday morning, and you can see there's like a lull in all your CW activity. And then as people are getting ready for the contest, it ramps up a little bit. People are checking out their equipment, getting ready to get in the air, and then boom, the contest starts. And there's a spike in activity on Friday evening, and then things drop off as you go into Saturday night and people go to sleep, and then things come back the next day. And you can see the RBN spotted about 12,000 spots just for this one period of time during the contest. So that's a lot of data. Above here, you can see this little dip here on Sunday. Above here, I have plotted what are known as either solar or geomagnetic. These are geomagnetic indices. AE is the auroral electrojet index. It's a measure of how much energy is in the auroral oval based on ground magnetometer data in the auroral oval region. And then the SIM-H and KP. SIM-H is a measure of whether or not you have a global magnetic storm, and this is measured from ground magnetometers at the equator, and KP is a general geomagnetic disturbance index. And most of you are probably familiar with KP, is that right? Have heard of KP? So generally if KP is high, like 5, 6, 7, that's when things go bad with the ham radio. And sure enough, you can look here on Sunday morning, KP goes up to about 4 there, and you also see this spike in auroral activity, and that geomagnetic disturbance is when the number of QSOs in the RBN goes down. So you can really see the influences of the space weather on the ham radio data, which is just really, really cool. Are there any questions so far? No? Okay. So I work at the New Jersey Institute of Technology, and one of the things we have access to is the United Astronomy Clubs of New Jersey Observatory at Jenny Jump State Forest in Hope, New Jersey. So it's maybe about an hour, hour and a half from here. It's a beautiful site, and it's a collaborative effort between amateur astronomy clubs throughout New Jersey. And they've got a clubhouse there where they actually have a lecture hall, and I gave a talk there about a week ago. And then they have these little huts where each of these has a telescope in it that different clubs from around New Jersey will maintain and run. And then this hut over here is different because that one's run by the New Jersey Institute of Technology. We have a LiDAR system in there. And when I started working at NJIT, my boss said, oh, you can go ahead and you can put a reverse beacon network receiver in there. So we have an RBN receiver there based on the red Pitaya using the same hardware I have in the demo station over there. And that's the hut there. And we have our antenna site up there. We just installed this last October. So if you go on the Reverse Beacon Network website and you look up K2MFF-2 or K2MFF-3, you can get live spots of what our RBN receivers are seeing in terms of CW from this site at Jenny Jump. And here we are. This is Josh, who you met before. He helped us install the equipment. Myself And then Ethan Miller, K8GU. He's an avid contester and a physicist at the Johns Hopkins Applied Physics Lab. And Gil Jeffer, he is our resident. His motto is anything worth doing is worth overdoing. I can tell you stories about that. He goes down to Antarctica every year and helps install and maintain the equipment down there. It's very interesting. This is what our reverse beacon network receiver looks like there on a rack. These are not great photos, but if you want to see what really looks like in person, just after the talk, come right over there. You can actually see the hardware in real life. So a little side sidestep tangent. So as a graduate student, I worked on a project called SuperDARN, the Super Dual Auroral Radar Network. This is a radar system designed to look at the aurora, and it operates between 8 and 20 megahertz. And in 2014, I had the opportunity to go down to McMurdo Station in Antarctica and help repair the radar system there. And while I was there, I was also able to operate the KC4USV ham radio station, which looks like this. It's a little airport electronics hut, runway electronics hut that they converted into a ham radio station. They have a little tri-band beam up there, I think, or multi-band beam. And I was able to operate there. And while I was operating, I made some recordings of myself, and one of those recordings was during a period of auroral activity. I'm going to play that recording for you right now. So in this recording, you'll hear me start by calling CQ. And when I'm calling CQ, it's just a recording in the room, not coming over the radio. So it's like hearing the side tone. So it'll be a pure, perfect tone. And then immediately after that, you'll hear the responses to the CQ, and you'll hear a tremendous amount of auroral flutter. And that's because McMurdo stations around here, that's because that during this time, there was a lot of auroral activity and auroral variability. Now the difference between this and if you're here and you say work aurora on 6 meters, here you're like pointing your 6 meter antenna toward the aurora and you're bouncing off the aurora, right? Here I'm actually operating on 14 megahertz and I'm transmitting through the aurora. So what you're going to hear, it sounds like auroral flutter, which is exactly what it is, but it's because I'm going through the aurora. And then you'll hear the aurora just calm down and you'll hear the tone clean up. And then it goes through. So I'm going to play that recording for you now. And there's my side tone. Did you hear it clean up? Yeah, I'll play it one more time. There's my side tone.
That's them answering you.
Yeah, that's them, man. A lot of variability, right?
I didn't even make it out.
Well, you just wait until... There, now you can start to make it out. Pretty neat, huh? Yeah. So that was a really cool experience. But it shows how much of an effect the upper atmosphere, the aurora space weather has on what we're doing. So
how often would that, like what was the interval of time before it went clean and then it got distorted and then went clean? I mean, was it a repeatable thing, or was it something that it would just during the course of you working the station, you heard that flutter that you can almost not hear it?
Yeah. Usually, if you have a geomagnetic disturbance, usually the geomagnetic disturbance lasts a few hours, a couple days, and then things kind of calm down again. One of the things the main mechanism that typically causes an auroral brightening is something called an auroral substorm, and that you'll usually have your most intense part last, say, tens of minutes to an hour or so, and then things will calm down again. So there's some really good videos about auroral substorms on YouTube, so I'd encourage you to look that up because it's really interesting to see the process of how the energy gets transferred from the solar wind into the Earth's magnetosphere and then gets dumped back into the auroral ionosphere. And you'll see why things are kind of operating on those timescales. Okay, so the reverse beacon network in FOF2. One of the things, so we have all this great data, but one of the things we're trying to do is puzzle out what's the best way to make use of this data. The ham radio data is a little different from normal scientific data in that it's really not designed for science, right? What's it designed for? It's designed for communication, for ham radio operators. It's designed for ham radio operators, by ham radio operators, and it's great for that. For science, we've been able to show that there are effects of space weather in this data set. But now, how do we actually make this data useful? So this is one attempt at trying to do this, and we have many attempts, but this is just an example of one way we might make this data useful, RBN FOF2. And so I already talked about the ionosphere. Here's a nice little cartoon of what the nighttime ionosphere and the daytime ionosphere looks like. And again, we talked about the layers during the day. You have the darn D layer, which absorbs a lot of our ham radio signals. And then you have the E region right above it, which you can sometimes get what's called sporadic E, but is actually probably less sporadic than you may think. And then you have up there, you have the F1 and the F2 layers, which at night combine into a single F layer. And one way you can characterize each of these layers is by what we call the peak density of that layer. So there will be a peak electron density of the D layer, the peak electron density of the E layer, and the peak electron density of the F1 and the F2 layer. And we have a way of converting that peak electron density into something called the peak plasma frequency. And one way we denote that, so like the peak plasma frequency of the F2 layer is something we normally call FOF2. It's the peak ordinary plasma frequency of the F2 layer. So that's where FOF2 comes from. So it's a number, and try and make that a little bit more clear in a minute. This is something called an ionosonde. I guess many people have heard of that before. This is a device used to measure electron densities in the bottom side of the ionosphere, and it does that by sweeping in frequency. So you might start at a low frequency, and you'll send your signal vertically up, and you'll listen for a reflection coming back down. And you can time the reflection. So if you know that your radio signal is traveling at the speed of light, you can calculate a height from which that reflection comes from. Now, in reality, the speed of the radio signal slows down as it goes through the ionosphere. So we call these heights virtual heights because we're just using the speed of light as a speed to calculate these heights. So you can sweep up, and you'll get to this. You'll get reflections down from the peak region of, the peak height of the E layer, and then you'll cut through that once you penetrate that plasma frequency. Okay, let me slow down again. Signals frequencies below the plasma frequency of a layer will get reflected back down. Signals above the plasma frequency will cut straight through. And so you'll hit the first plasma frequency of the E layer here, you'll get reflections down, and then you'll get up to the F1 layer, you'll get reflections back down, and as you keep sweeping up in frequency, you'll get reflections from the F2 layer, and you'll be able to measure that. And so this is what the ionosonde does. It just sweeps through these frequencies, and then you can measure these peak plasma frequencies along the way. You can get a lot more information out of ionosondes, but that's, for the purposes of this talk, that's good enough. One issue with ionosondes is they're very big and they're expensive. So this is a small ionosonde, which is about 15 meters tall and 45 meters long. And it's carefully calibrated and set up, and you can do a lot of really good science with it. But you can't put these everywhere over the US or over the world, and you can't install them in the middle of the Atlantic Ocean. So the places you can get measurements from this are limited. So what if we were able to use the reverse beacon network to make measurements similar to an ionosonde to get this plasma frequency. Then we would have, like say during a contest or during a period of high activity, we might have the ability to get measurements of the ionosphere from over a very large geographic area with pretty good spatial coverage, much better than just the few ionosondes we have scattered around the world. So that's what one of the things we're trying to do with the reverse Beacon network. And one way we can do that is something called the Secant Law, which says you take your maximum usable frequency, which is the highest frequency you can use to communicate from one point to another, and you can multiply it by the cosine of the reflection angle between your transmitter and receiver, and then that gives you your FO value. And so what we do right now is we assume a height for the ionosphere for the reflection, and we can get transmitter and receiver locations from the reverse Beacon network and by doing QRZ lookups, and then we can calculate this number, and then we can make maps of things. So this is a map of reverse Beacon network data color-coded by frequency during a 15-minute period during the 2014 November sweepstakes. And I've divided everything up into grid squares here, so your regular Maidenhead grid square system. And in each grid square, I find what is the highest frequency observed there, and I use that to determine my my maximum usable frequency for the grid square. And then I look at where the transmitter and receivers were, and I assume a height for the ionosphere. And then we can estimate that reflection angle. And then we can use that formula I just showed you to calculate a map of estimated FOF2 values. And it's, there's a lot of assumptions in there. There's a lot of things that we are guessing about. But it actually does pretty well. Because one of the things you'd assume, or you'd expect, I shouldn't say assume, one of the things you'd expect is to have lower FOF2 values at night and then higher FOF2 values during the day. And on this map, you see that very well. I have the gray shaded area over here, and you have these blue and purple values showing the very low values. And you have the daylight over here, and you have these green values. And you actually have a nice smooth gradient right across the way. And so that's very promising. And along with that, actually, here I have a movie of the entire weekend. So I'll just play the movie for you, and you can see how that changes with time. So there's night, and you're capturing those lower values. You can also see at night when the operators go to bed, you get less data. And then when daytime comes, you get the higher values. And you get a lot of data when people are very active, and then at night, it's lower values again. And each of these little purple triangles here, that's an RBN receiver. So you can see what the distribution of the RBN receiver network looked like as of 2014. I don't think it's terribly different right now. So one thing you can see is that we have a lot of RBN receivers on the east coast, east of the Appalachians and west of the Appalachians, and not a whole lot over on the west coast or in the middle. So I'm looking for more people to set up RBN nodes, but I should really be giving this talk, say, out in, like, I don't know, in Kansas or someplace out in the Midwest to motivate people out there to put up more of these things. But you do get some very interesting data. Looking at that a little bit more closely, we can zoom in on one particular grid square. This is looking over Wallops Island, Virginia. And NASA has a flight facility there. And we actually have a super darn radar there. And there's also an ionosonde. And so we can compare the measurements made by a real ionosonde with the estimates made by this algorithm. And they're actually in pretty decent agreement. So you can see the green, this green dark color here, fuzzy thing, this is the ionosonde measurement. And then the blue with the error bars, larger error bars, is the ham radio estimate for that particular grid square. And you can see that we track the overall trend fairly well. And so this has at least some promise in terms of giving us gross measurements. These measurements aren't perfect, but as I said, if we have a lot of them, where we don't have any measurements, this could still be helpful in constraining certain ionospheric physics problems. Josh over there, he took that algorithm that I just showed you, and he wrote a visualization code to let us see this in real time. So we actually have a web server running where you can go to and you can see the result of that algorithm pulling in data in real time from the reverse beacon network and showing that on a Google Maps API. And so you can actually see that in real time. A little bit more about this ham radio data. This is really a big data problem. So the RBN is not the only game in town. There's also something called WhisperNet, which many people here have probably heard of, the Weak Signal Propagation Reporting Network that started in 2008. There's currently, or from a few months ago, there were about 535 million spots in that network. And then that's a database size of about 44 gigabytes. The Reverse Beacon Network has 578 million, goes back to 2009. And PSK Reporter, every time you make a PSK QSO, that gets logged by this one, and that has 1 billion spots in it, and that's only from 2013. So it's a lot of data. How many people here use FLDigi or DM780? So we've got a few people. Did you know that if you dig into your options in one of those programs, you can actually send all of the signals that your waterfall spots to PSK Reporter? So if you don't already do that, go into the options of your PSK or other sound card digital mode program and see if you can figure out how to send your spots to PSK Reporter. And that not only helps our cause, but also helps other ham radio operators, spot you. And spot each other. So that's really cool. And you can go to any of these websites and you can go look up yourself, just Google PSK Reporter. You can see them spot you and who heard you around the world. So that's really cool. So the takeaway from here is there is a lot of data. And this is not a very traditional experiment. Normal science, you say, OK, I'm going to design an experiment to answer I'm going to come up with a hypothesis, design an experiment to answer that hypothesis. Here, we kind of have a data set that was given to us, and now we are trying to figure out how do we mine information out of this data, how do we come up with hypotheses that this data can answer. So we're always looking at ways to improve the existing techniques and develop new ones. So in the last part of this talk, I'm going to talk about the Great American Eclipse. Does anyone know what's happening on August 21st, 2017? There's a total solar eclipse. That's right. It's not just any total solar eclipse. It's the Great American Eclipse. And that's because it's going to start, totality is going to start in Oregon and go all the way to South Carolina. It's going to do that in just 90 minutes. And even if you if you want to see totality, you have to be within these two little bars. Now we're up here in New Jersey, so you either have to travel to see totality, but let's say you're not lucky enough to travel, you'll still be able to see a partial solar eclipse. I think about 75, maybe 80% solar eclipse here in New Jersey. And Josh is going to be giving a talk, and he'll be up at the NJIT Observatory. So if you want to go hear him that weekend, you'll be able to go do that this summer. But yeah, there's going to be this total solar eclipse, and the eclipse is going to cause the shadow of the moon to cover the Earth. And that, of course, that has a great optical effect, but what else do you think it affects? It affects the ionosphere, it affects radio. And there's actually evidence already. This has been studied for about 50 years so far, maybe even more. But this is an example from the eclipse in the UK, August 1999. This green data is Asonde data, and this blue data is a prediction from an ionospheric model called the International Reference Ionosphere. And it's a computer program that uses empirical data. You can put in a date and time. It'll give you a prediction of what the ionosphere should look like. So the IRI does not have the eclipse in it, and the green is actual measurements from an ionosonde. And you can see that the eclipse deviates from the predicted non-eclipsed version for about 2 hours. It drops down a whole megahertz in FOF2 value. And that's kind of interesting because totality only lasts like 2.5 minutes. But really the effect on the ionosphere is much larger than that. And I think part of that is because you actually have this very gradual, the shadow comes over very gradually, and then all of a sudden there's a very steep darkness, and then it returns to daylight very quickly, but then there's also a period of gradual recovery after that. I think that's reflected in here. But you see that there's quite a dramatic effect on the ionosphere. And then this is an electron density model done for that same eclipse. This is the UK over here, I think, and this is pretty much all of Europe. And you can see that the eclipse causes a very dramatic effect on the ionosphere. It's quite large, covering almost all of Europe. This is estimating electron densities at 280 kilometers altitude. And so you can see it's a nice big hole there. And this is great, but for only recently have we had the tools to be able to do large-scale imaging of the ionosphere. For many years, people have studied these eclipses and their effect on the ionosphere, but they'll have like one radio here, another radio there. They'll just be making point measurements. They didn't have the internet. They didn't have lots of people with hardware that could go out and make measurements. They didn't have networks of GPS total electron content receivers. Now we have all of these things, but eclipses are fairly rare. They happen, either total or annular eclipses happen twice a year, but often not in places where we can get to them, where we have good instrumentation. That's what makes this unique. We have a great coverage. The eclipse goes over a large area where we have lots of instrumentation, lots of ways to look at this. So the scientists at Virginia Tech, they're going to be studying the ionosphere using mostly professional techniques, using the super darn radars, total electron content receivers, ionosondes. They're going to be working with the Millstone Hill radar in Massachusetts with the MIT people. But we always need new ways of looking at these things, and that's where the ham radio operators come in. We have a real opportunity to make interesting measurements. And one of the things I think would be interesting would be to create a contest-like event to help image the ionosphere using these data sets. And so that's why we have this thing called the Solar Eclipse QSO Party. And what we want to do is we want to flood the HF airways with signals during the eclipse. And so by generating lots of QSOs, we should be able to image the ionospheric changes. And so we will be having a Solar Eclipse QSO Party. That's going to be August 21st, this August 21st from 1400 to 2200 UT. And that corresponds to about 2 hours before the partial eclipse hits in Oregon. And it corresponds with about 2 hours after partial eclipse ends in South Carolina. So it covers the entire US. And you'll get, it's contest-like, so you get 2 points if you do CW or digital QSOs. You get 1 point for phone, and we're going to have multipliers where you multiply your score by the number of grid squares. So the exchange is going to be your RST and your 6-character grid square. And then all of this is going to feed into, of course, reverse beacon network, PSK reporter, WhisperNet. And then also, we'll want you to submit logs as well. And we'll have that up and running on our website for log submission. And that way you can tell us exactly where your transmitter is located during the eclipse. And if you go to hamsci.org/SEQP, you can get the full rules. Yes?
Real RST, not 9x5.
Yes, yeah, it would be good. I'm uncertain about that because the RST is very, very subjective. We do have real RST up there, but these networks, especially if you're using the digital modes, they're going to be also recording an actual value. So I'm not sure how valuable the real RST is going to be. Yeah?
So I'm assuming that, say you can't participate actively,
Uh-huh.
you can set up like a whisper beacon to still contribute data, essentially?
Absolutely, yes. So if you cannot participate actively, you can set up a WhisperNet node, which if you already have, Digital Master 780 or FLDigi, if you know how to set up in a wideband mode and click that button to send your spots to PSK reporter, that's a contribution. Just leave that running. If you have, if you want, I'm showing people how to set up an RBN node over there. If you're interested, if you participate in frequency measuring tests or things like that, we're working on ways that you could participate and send data that way as well. So there's a lot of different ways. So the Solar Eclipse QSO Party is just one way. We have bonus points available. So if you operate during totality, you get 100 points. Operate outdoors so you can see the eclipse, you get 100 points. Public venue, 100 points. Provide detailed station operation information, you get 50 points for each of these different things like antenna characteristics and terrain profile. If you operate one of these systems, PSK reporter or WhisperNet or RBN node, you get points. You also get points, this is different too, you get points for being spotted by the spotting networks. So this is kind of fun. Normally in a contest you actually have to be making QSOs to get points. Here you just need to be spotted by these networks and you can actually get points for that as well. So this is the HamSCI website. So I was the major person who started this organization, saying I have this vision for an organization that connects the ham radio community with the professional researchers. And I worked with a number of people at Virginia Tech and the American Radio Relay League and other places to get this going. But for all intents and purposes, I wrote this website, put it together, and I'm the main organizer of it. And so HamSCI is a ham radio science citizen investigation, and our goal is to advance scientific research and understanding through amateur radio activities, encourage the development of new technologies to support this research, and provide educational opportunities for the amateur community and the general public. So this is a very broad organizational charge. So the Solar Eclipse QSO Party and the Solar Eclipse activities are just one project that falls underneath this. But we try and incorporate all sorts of different science projects that study the ionosphere and that meet these goals. We have people from many institutions around the world who are doing different sorts of science projects. A couple years ago, my friend Gareth he's now at University of Calgary, I believe. He had his EPOP satellite fly over field day a couple years ago, and he listened to CW signals with that, and we're still working on analyzing that data, and he might do that again this year. So hopefully we'll advertise that through this and through the American Radio Relay League. I know some of the people here were interested in doing some STEM partnerships with local schools. We could potentially talk about how we might be able to bring the science that HamSCI is doing and have that be incorporated in a public school STEM program. I think there's a really good opportunity for a joint partnership there. Fortunately, we're not alone in doing this work. The AWRL has been very gracious in providing us with public relations. They've given us QST articles, and we have fairly regular QST space right now, which is very nice. They also provided us with a booth and sponsored a forum at Dayton this year, so we had many people participating in that. So the AWRL has been great in helping with this effort. And I just wanted to give another plug for the NJIT Club, which is where I work and where Josh is a student. We're a nice active club. This is a photo taken after the New York Marathon this year, so that's why it's dark, and you can see all the members we have there helping out with the public service communications at the New York City Marathon. We have some students who are operating a contest earlier this year. Josh and Brendan are working with some Morse code keys and soldering irons. So it's a nice active club. We have a nice station, and it's a good place for people to come and learn about ham radio. So in summary, ham radio and space weather, we routinely as hams communicate using the HF bands. The RBN automatically monitors Morse code and digital HF communications, and then we also have the WhisperNet and PSK reporters also contributing to their own data sets. Space weather activity routinely affects HF communications and RBN and other network observations. we can estimate the FOF2 parameter using RBN data. And we have this total solar eclipse coming up this August 21st. And the shadow of the eclipse is going to stop the production of ions in the ionosphere. And the HamSCI and the AWRL will be promoting a solar eclipse QSO party to help generate data during this event to study the ionosphere. And these networks that we talked about before will create a citizen science data set that we, as scientists and as amateur radio operators, you can download this data too, can analyze and try and see how the solar eclipse is affecting the upper levels of our atmosphere. So that, I'd like to thank you very much for your time, and I encourage you to come back and see our demo. Are there any questions?
What did you say?
Are there any questions?
Can you translate the universal time to like
Now?
Yeah,
So, right, so in the summertime when we're in daylight savings time, you just add 4 hours to our local time here on the East Coast, and you'll get UT time. And if you, in the winter when we're on Eastern Standard Time, then you add 5 hours.
So it starts at 10 a.m. for us, basically.
Yeah. Yeah. So that UT time is the same, like Zulu time, UTC, GMT that you hear, and it's the same time you're supposed to be writing down in your log books when you're logging QSOs.
Does it have to be multiple choice or essay?
It's fill in the blank.
Did you get N1MM and 3FJP on board for
I think
contest to be supported?
N1MM said they would support our contest.
Okay.
So we said we would finalize our rules by July 1st. So we're quickly approaching that date, and then they said they would implement that after July 1st. So watch our website for more details.
Cool.
You get more points if you actually drive into the area of total darkness and operate there.
That would be nice, but no, we're not making that. Yeah. Well.
Oh, you should, because it's
Well, I guess you sort of do get extra bonus points because 100 bonus points are given if you operate during totality, right? So you can't really get those bonus points unless you're there.
Oh no!
See, I got
Now we lose out though,
Ah.
because we're only like 75% up here.
Yeah.
Yeah.
Road trip?
Yeah, road trip. I got a beer.
it's a Monday. By the way, it's a Monday.
Yeah.
It is a
It's
Monday.
a meeting day, you know.
Yeah, work's overrated.
Yeah. Well, we tried rescheduling the eclipse, but they said no, so we're stuck. So, okay, well, thank you very much. As I said, please come to the back. We'll be there for a little bit. We have a demonstration RBN station over there. Josh is very good at explaining it, and I can explain it as well. It's red pitaya based, so this is a really interesting thing. It looks kind of like a Raspberry Pi. It's not designed to be a radio, but using special software, you can turn it into a radio, and it can monitor 6 HF bands simultaneously, which is like the entire CW portion of 6 HF bands simultaneously, and decode all of that and then send it up. So it's a really neat system. So thank you very much.